So our next presenter is Dylan Shimmi. He's a third-year student studying electrical and electronic engineering. His supervisor, primary supervisor for this project is Lucy Forman. Daniel and I have been supporting this project from the HIVE side, and Ellie Sampson has also been providing some support as well. And this is all about 3D scanning of meteorites. So over to you, Dylan.
Hey everyone, my name's Dylan, and today I will be discussing my project where I had to 3D scan meteorites using photogrammetry. So in popular culture, many of you would have already had an idea of how meteorites and meteors are depicted. You may see them being depicted as these glowing space rocks that come from a mysterious place out of space, crash into the Earth, and maybe even give people superpowers. Unfortunately, meteors and meteorites don't give people superpowers, as much as I wish they did. But they're still quite important to researchers. Now, why is this? So, one of the big questions that researchers have is actually understanding what our solar system is made up of. And by studying meteorites alongside with meteors, researchers are able to understand, firstly, where it came from in space and its orbit, and the way that it burned through the atmosphere as it traveled down into Earth. And this can help answer the big question, as meteorites are quite old, so their chemical composition could reveal information about what the solar system was made up of. And just in case any of you were unfamiliar, a meteoroid is essentially a space rock in space, so that one there. A meteor is when the space rock essentially travels through the atmosphere of the Earth, and a meteorite is when it lands on the Earth, right? So researchers want to be able to 3D scan these meteorites, and a common way of doing this is with photogrammetry. But what is photogrammetry? Essentially, the idea is we take a bunch of photos of the subject with the camera. You need to have a significant overlap of the subject in the photos, and you need particular camera settings in order to do this. But the idea is, if we take a bunch of photos of the subject at small degree increments, and provided that they have enough overlap and that there's enough coverage, we can use particular photogrammetry software in order to reconstruct the model based on those images. So why are we 3D scanning these meteorites in the first place? And why with photogrammetry? Well, to answer that first question, 3D scanning provides a way of creating a digital twin, almost, of the meteorite. So researchers can essentially have a digital version of that meteorite available for visual analysis, while also being able to break apart the original meteorite for chemical analysis. And that is a lot more efficient and allows for a lot more freedom and flexibility with how researchers analyze meteorites. Now, in terms of photogrammetry is actually very cheap when in comparison to other methods of 3D scanning, like laser scanning or CT scanning. The major costs of photogrammetry are going to be a camera and the equipment that you're going to be using. And finally, photogrammetry is a great way of showing details on the surface of the meteorite. In comparison to other methods like laser scanning or CT scanning, we are able to see a lot more details on the surface of the meteorites. And this can be great for that visual analysis that researchers want to be able to do. But what's the problem here? So the current method of photogrammetry is with a manual photography process. So what this looks like is essentially we take a photo, you move around slightly, you take another photo, you move around slightly, you take another photo. And you have to do that all around the meteorite, then flip the meteorite around and do that whole process again. As you can imagine, that's a very manual process, but it's also quite time inefficient, right? And very labor intensive. The other problem is that because it's such a manual process, there isn't really enough room to implement techniques that can increase the amount of details in the photos. And so when we process these photos in Metashape, we'll end up with models that aren't quite in high quality. So that's kind of what our project is about. We're essentially going to be developing 3D models of meteorites as a proof of concept of this workflow, but more importantly, designing that workflow that researchers could use to essentially 3D scan meteorites as they fall into the Earth and get recovered. So here's the method. So the first stage is essentially the photo taking process. Essentially what happens is once all the photos are taken, we process them using a technique called focus stacking, which I'll get into a bit later. And finally, we process those focus stacked images into a software called Metashape. So for the photography, we used a Canon 5D Mark III. This is a 22.3 megapixel camera, and we use a 24 to 105 millimeter zoom lens. We used an LED ring light to provide some lighting, and we had this supported on a tripod for stability. Now, there were 4 particular camera settings that we needed for this photogrammetry. The first one was the ISO. Now, essentially what ISO is, it's basically how sensitive the camera is to light. So the higher the ISO, the more light gets picked up in the photo. But if you have too high of an ISO, you start to introduce these sort of grainy noise textures in your photos. Any of you who've ever taken a photo of the night sky might have seen, or on your phones, you might have seen how there's a bit of a grainy sort of noise appearing in these photos, and that's something we want to avoid altogether in photogrammetry because those noisy textures appear on the final model. The next part is the aperture. So essentially the aperture is basically how much of the image is how much of the subject is in focus at a time. Now, normally you might think you want to make this as high as possible, but if you have too high of an f-stop, you end up with a phenomenon called diffraction blur, which is essentially where the entire image gets softened as a result of having such a high aperture. Too low of an aperture and you won't be able to get enough of the image in focus at a time. So we have to settle for the middle of the range that was available for this camera. So that was f-stop 8 to about f-stop 16. We used a custom white balance. So white balance is essentially the camera's way of calibrating the color so that it appears as it does in real life. And this was set to custom because it was dependent on the room light and the lighting conditions. Finally, the shutter speed was set to variable. So essentially, this depended on essentially just depended on the meteorite and the lighting conditions. Okay, so the next step is focus stacking. So I talked a bit about earlier in the method section, but what focus stacking is, it's basically a technique that's borrowed from macro photography. So the idea is if we have a camera and we take photos at varying distances to the subject, you get different parts of the subject in focus in each of those photos. The idea is if we take a bunch of these photos and then combine them together, we can get one image where everything is in focus. So that there, you can see how the front of that meteorite is in focus, while the back is sort of a bit blurry. And in the second photo, you can see how the back of the meteorite is in focus and the front is a bit blurry. And in this photo, that's the combination of these 2 photos together. So everything is now in focus. So the next part of this project was the stack shot machine. So what is the stack shot? It basically contained 3 important equipment that we had to use for photogrammetry. The first one was the macro rail. And what this does is it moves the camera along, then it allows the camera to take a photo, move it along, take a photo, move it along, take a photo. And this is essentially focus stacking, right? So it's moving the camera along certain distances closer to the subject, and it's performing that focus stacking. Once it's completed a certain number of stacks, it'll move back to the original position and then rotate the rotary table. So the rotary table is basically a turntable with a motor mechanism in it. And so this motor mechanism can be rotated at very small degree increments. This can all be controlled on the stack shot controller, right? And you can set a program to set the number of steps that the macro rail performs, and you can set the degree of rotation on the rotary table, as well as how many rotations you want on that rotary table. So here is a video of this thing. Yeah, so this isn't 2 times speed, by the way, but so you can see how that macro rail is moving, taking a photo, and then does it again, and then moves it back. And then you can see the rotary table moving there. Right? So it's doing that, moves forward, and then moves all the way back, and then rotates the table there. And so on average, we had about 10 of those steps for focus stacking, and we used a 10-degree rotation on the rotary table. So that was 36 different intervals in total. Okay, so once, actually before this, we'd have to rotate that meteorite around and redo this whole process once we completed that one revolution. But once we've taken all the photos, we essentially process this in a software called Helicon Focus. And this essentially combines all those photos together to create those focus stacked images. So you can see on the left, this is the image that was taken with the camera, where you can see that the back's more in focus than the front there. And this is the focus stacked image. So this has used 11 photos, which you can see up here. And these are all the photos that we used for the focus stacking. And finally, the last step is the photogrammetry software. So essentially, we used a software called Metashape to create the model. And Metashape follows a 4-stage process. The first stage is aligning the photos. So aligning the photos lets the software know where the camera positioning is relative to the model. You can see there all of the camera shots around these points here, which is basically the points that it uses to create that model. The next stage is it creates the depth maps. Now what depth maps are is basically just telling the software, recognizing how far away certain parts of the image are to the camera. In this third stage, we create the model, and you can see already how the model has got that sort of complex shape, right, around here and around here, right? And finally, we build the texture. Now, the texture is heavily dependent on the quality of how blurry the images are. So if the images are in focus, they're completely perfect, you'll get a very good texture, right? And this is why I said earlier we wanted to incorporate techniques that increase the amount of detail you can see in the photos. So these are some of the results of the project. Essentially, these are pretty high quality. You can see how they're quite complex, and essentially there's a lot of complex geometry, good texturing, and nice colors. So, one part of the project's been completed, the high quality models. But in terms of the workflow, so with the old manual method of photography, you could get 127 photos, roughly that much, in about 2 hours. With our process, we can take about 1,080 photos, right? And this translates into 108 focus stacked photos. And we can do this in the same amount of time. So that's roughly 8 times more efficient, right? It's pretty good. So there were some challenges that came with this project. I mentioned briefly how after it's imaged one revolution, we'd have to flip the meteorite around to capture the other side, right? But the issue with that was, well, the problem is that we couldn't, basically because we didn't have a 3-axis system, we had to do that rotation manually. So that was kind of a bit of a bummer, really. We couldn't figure out how to do that 3-axis system. The second part was that we weren't able to verify volume calculations. So essentially, I had a workflow designed to be able to measure volume, but the problem was because the meteorites didn't have their volumes measured previously, we weren't able to determine whether the volumes calculated were accurate or not. And so finally, the last point was essentially during some of the circuits, we noticed that parts of the model weren't quite imaged properly. And in particular, these were holes and crevices. So we had to design a separate method in order to be able to essentially image these holes and crevices. So what it is if you, okay, so that hole there, you can kind of see, it's a bit hard to see, but it's not quite imaged properly, right? And so what we had to do was we came up with a way of essentially it's focus stacking, but on a mini version, on a mini scale, right? So instead of focus stacking the entire meteorite, trying to get the entire meteorite in focus, we'd instead try to just focus stack the specific hole that we wanted to image. So you can see in this image, the hole there, the hole there is completely in focus, while the texture around that is blurry. And you can see essentially which holes needed to be imaged from the confidence model, which tells you how well Metashape used the images to reconstruct that part of the model. So you can see here, these red spots are essentially where Metashape couldn't reconstruct that model properly. So anyway, we essentially developed this technique by looking at this confidence model, performing focus stacking on these holes, and essentially what we would do is we would mask out everything apart from that hole. And what that would allow us to do was, when we put these photos into Metashape, Metashape would recognize that, oh, okay, I only want to actually use the hole as part of my model reconstruction instead of modeling that entire surface of the meteorite, as it is quite blurry, so you'll end up with blurry textures otherwise. And so as a result, we were able to pretty much image the holes quite well. So what are some future opportunities for this project? Well, one potential opportunity I see is being able to develop that 3-axis system so that we can turn this project from a semi-automated workflow to a completely automated one. The next thing I'd like to see are maybe some Sketchfab links. So putting these models up on Sketchfab to allow researchers from all around the world to be able to visually analyze these meteorites. I'd like to see an interesting application with VR. So something I was thinking of was essentially having the meteorite inside in VR, being able to see that photogrammetry scan on the surface, but looking inside of that meteorite and being able to see the CT scan, which unveils all of the chemical composition inside of that meteorite. And finally, I could see this being used for educational purposes. So something I was considering was maybe having these 3D models be available in geology labs, so that and letting students being able to essentially analyze these meteorites, identify particular features, and essentially and maybe get an idea of how the meteorite burned or the meteor burned through the atmosphere. That'd be a really good way of teaching students. So in conclusion, we were able to develop a 2-axis system. We did this with high quality 3D models, and we designed it with an efficient and reasonable workflow. So there were some challenges that came with this. Some we managed to overcome, but others we weren't able to. And I'd like to see further future opportunities try to overcome those challenges we weren't able to. And just as a bonus, so you can see here, these two are the same meteorite, but this one was imaged with the old method. You can see how the cut surface there is quite bumpy, right? Which is not what it looks like. In comparison with this new method, you can see how that surface is completely flat, right? So it's essentially a much better version of that version. It was much more well imaged. So that's it. Thank you.